I'll be speaking to you about Bayesian optimal design, experimental design, and I will focus on mainly on multi-level Monte Carlo for this particular problem. So I hope you have some background on multi-level Monte Carlo. If not, I still will be giving some underlying ideas. And just a second. Yeah, you can see my screen, right?
Yes, that's fine.
Yes.
Okay. So this work is based on 3 papers, and I will show them at the end, the titles and everything. So the idea of optimal experimental design is to find a design that maximizes the success of an experiment. And of course, we do not want to perform the real experiment before we know what is the best one. So that's why this is called a model-based approach. So we are using some mathematical models to find what is the best experiment we need to use as a real experiment. So for that, we use a data model assumption, which tells us basically the data Y given an experiment xi, and here xi has a very broad meaning. It could mean anything that defines the experiment. It will be defined, this data will be defined by a mathematical model G plus an additive error, which is zero mean Gaussian with a covariance sigma epsilon. Here the inputs for G are theta, which is a random variable, and this random variable basically defines the parameters we want to recover. And so if you think of a physical problem, theta, it's actually a deterministic variable, but given the lack of knowledge we have on the problem, we think of theta as a random variable because we want to recover it. And of course, this experiment can be done many times, and we can have repetitive experiments. So we collect these experiments in what I call here capital Y. And the total number of experiments is NE, and of course we don't change the experiment. If we are going to perform this experiment, let's say 10 times, we keep the model fixed, but we sample again and again the error. So it's quite usual to use the information gain here called Kullback-Leibler divergence, which somehow measures the discrepancy between our knowledge prior to the experiment and posterior of this experiment. So here pi of theta represents our knowledge prior to the experiment. So is what we know beforehand. And after we collect data, after we perform the experiment and we have measured the variable Y, which is our data, we can improve our knowledge and compute the posterior. And to compute the posterior, we use the Bayes rule. And with these two quantities, we can somehow measure this discrepancy or this gain, if you will, that will tell us the information gain. What was the gain by performing this experiment? Okay, so here we have in the Bayes rule the likelihood, which is P of Y given theta. And we have the evidence, which is basically a normalization term, which is the integral of the likelihood times the prior. And the tricky part in multi-level for this design of experiment is actually the inner integral, which is this evidence here. Of course, we can compute this DKL for many different outcomes, say I, and we can integrate this DKL over the whole space of Y. And that is what we call the expected information gain and the note by I. This I depends only on the design Xi. And it's basically this double integral, which here is in blue and red, and with the inner integral in the denominator. The likelihood here, because of the model we assumed, is a normal distribution centered on G, and it takes the form of this last equation. So just to motivate a bit, let me show you here the one experiment that is the electrical impedance tomography. And here we have a laminate composite material. This is a cross section. And on top, we have electrodes as well in the bottom. And this composite laminate is very simple. Actually, it's made of 2 plies. And these 2 plies, they contain fibers oriented with some direction. And we want to recover the direction of these fibers. So the red electrodes, they are current influx, and the blue ones are current outflux. And on top, I am showing the best experiment we could find, assuming that our variable here, our design, is the position of the electrodes. On the bottom, we have the worst experiment. And here I show you the surface corresponding to the expected information gain for many different experiments. And here Xi1 and Xi2, basically these 2 variables represent the shift between the electrodes and the distance, the shift between the bottom electrodes and the top electrodes, and the distance between the electrodes. And as you can see, the best experiment is on top, and I am showing the posterior there, is quite concentrated. That means that we can recover quite well the orientation of the fibers. And on the bottom left, I have the posterior distribution of the worst experiment. And as you can see, there is in one direction, we cannot recover quite well the orientation of the fibers. So let's now, that was a motivation. Let's enter in the double loop Monte Carlo estimator for the expected information gain. So as I told you before, we had 2 outer integrals, and these 2 outer integrals can be integrated using a Monte Carlo integral, which is here over the index n. And the inner integral, we have here another Monte Carlo with the index m. So this the work of this estimator is basically n times m. In this case, likelihood evaluations. So this can be quite expensive, right? Here there are no tricks. This is just plain Monte Carlo applied to both outer and inner integral. So usually Monte Carlo estimators, they are known as unbiased estimators, but of course here, since we have a nonlinear function, actually 2, the logarithm and the 1 over the inner integral, we have a bias. And this bias is actually proportional to 1 over m. And the variance of this estimator has the classical component of Monte Carlo, 1 over n, but has an additional variance owing to this additional Monte Carlo, which is proportional to 1 over n times m. So this is not an unbiased estimator. It is consistent though. Consistency means that as you increase the number of sample, the bias vanishes. Okay, we now aim at defining a tolerance. And for that tolerance, we want to find the parameters m and n that minimize the computational work, satisfying this inequality in probability, the probability inequality, which says that the probability of this error being larger than the tolerance being smaller than the tolerance is larger than 1 minus alpha. And alpha here is a very tiny parameter, which is larger than 0. Okay, here I show how we split the error. Basically, we have I, our real expected information gain, minus the calligraph I, which is our estimator. Using triangular inequality, we arrive at two components. One is the bias, the blue one is the bias, and the red one is is the statistical error. And using the CLT theorem, the central limit theorem, we arrive at the last equation, which is at the last inequality, which is a constraint on the statistical error. Of course, this is satisfied in probability. So we have a confidence parameter here, which is C alpha. As I said, we have an optimization problem to find M and N. And if we minimize this work, given the constraint, the bias and the statistical error constraint, we arrive at these two quantities, N and M, given N proportional to tau to the minus 2 and M proportional to tau to the minus 1. And that in total gives us a work proportional tau to the minus 3, which is quite expensive and of course worse than plain Monte Carlo, which is tau to the minus 2. So I have to talk about a particular ingredient here, but I'll be really quick here. This ingredient is crucial to have a good multi-level Monte Carlo estimator, double loop estimator, and it's the Laplace approximation. We use the Laplace approximation as a change of measure, and this is the Laplace approximation of the posterior distribution. We call here pi tilde, and pi tilde is Gaussian, and this can be a good approximation if the actual posterior can be well approximated by a Gaussian, of course. And theta hat here is the maximum a posteriori, and sigma hat is the covariance of this Laplace approximation, which is obtained using a Taylor expansion of the log likelihood. So here I just show you in the evidence, for instance, how we do this change of measure. Basically, the change of measure, it's a multiplication by 1. So we don't change the value of this integral, but we do change is the variance of the estimator of this integral. So as you see, we multiply by p tilde and divide by p tilde. And in the inner loop, we see here that we have this blue and red term, which is our important sampling for the inner loop. So of course, there is no additional bias because we assume they have the same support and it's just a multiplication by 1. So again, the work is still tau to the minus 3. So let me show you what is the effect of this change of measure with this simple model, which I will not describe because it's pointless. But if we compute the total work in seconds here, we have the dashed blue line showing the work of the classical double loop Monte Carlo that grows with tau to the minus 3. And we have the double loop Monte Carlo importance sampling, which is the solid red line growing with tau to the minus 2. And of course, this happens for the important sampling here, we expect tau to the minus 3, as I told you, but we see here tau to the minus 2. And this happens because the important sampling is so good that the inner integral is basically up to a tolerance 10 to the minus 3, roughly, is computed with only one sample. Of course, after tau to the minus 3, we will get the rate tau to the minus 2. Sorry, tau to the minus 3. Here on the left, I show you the optimal N and M for one experiment, and on the right for 10 experiments. So you see that N grows with tau to the minus 2, M grows with tau to the minus 1, but with important sampling, it doesn't grow up to, in this case, tau to the minus 3, and in this case, it doesn't grow up to the tau to the minus, sorry, tau to the minus 2, and here tau to the minus 3. So as we increase the number of experiments, the Laplace approximation gets better and better. And this is a consistency plot showing that as we decrease the error, as we decrease the tolerance, the error decreases consistently. So now we enter in the double multi-level Monte Carlo. So we now assume that the mathematical model G cannot be computed exactly. So we need a numerical discretization for this G. It could be finite differences, finite elements, finite volumes, or spectral elements, whatever you need to solve this problem. So you have an additional error. And now we only have access to GH, which is in an approximation of G. And this H makes reference to the mesh size, okay? Because we mainly work with finite elements. So then we have two assumptions here, which are really important for the multi-level Monte Carlo estimator. So the first is the weak error, which is the bias. The bias should be ordered h to the eta w. Eta w is a positive parameter here. So that means that the bias should decrease as h decreases. And we have here the computational work of GH, which grows with h to the minus gamma here, and gamma here is positive. So if we plug the approximated model, the likelihood looks basically the same, but we have here now the model GH, okay? So for this problem, we can do basically what we did before. We try to find the N and M, the optimal number of inner and outer samples. We can do the same here. And we can do the same with kappa, which is the splitting factor between the two errors. And subject to the bias constraint and the variance constraint. So if you check here on the right, the bias constraint, we have the additional term related to the mesh discretization, which is CW times H of to the eta W. And if we solve this minimization problem, we arrive at the parameters N and M as we did before, again, tau to the minus 2 and tau to the minus N, but we also find the mesh discretization that we need for this tolerance. And it should scale with tau to the 1 over eta W. And the total work now gets a bit worse because we have this additional bias, and you see that it's proportional to tau to the minus 3 plus gamma over eta W. So this gamma over eta W usually is around 1. So that means tau to the minus 4. So it's quite expensive to solve this problem for small tolerances. So let's define now the functional Z that depends on the random variable theta. Okay, this is, we define this functional as the expectation of f of y, and f is the log ratio between the likelihood and the evidence. And to make everything crystal clear here, we replace all the models here to show you how the numerator looks and the denominator. As you can see, the numerator does not depend on the model because the P of the likelihood P of y given theta, given our model, y is computed with theta. And when we condition on theta, this we end up with the distribution of the error. On the other hand, in the inner loop, we have the theta that comes from the outer integral and the theta prime, which is a dummy variable in this integral. And then we have to compute the model here in order to compute this integral. And we can reformulate the expected information gain as the expected value of this z functional. So now let's formulate properly the assumptions for the multi-level double loop Monte Carlo estimator. And the weak convergence basically here is the norm of the expected value of the difference between GL and G, where the metric is the inverse of the covariance of the error. And this should decrease with h to the eta L. And here L is a sequence of discretization levels. The strong convergence, in a similar fashion, we have the expectation of the norm of the difference between GL and GL minus 1 to the P, and outside we have to the 1 over P. And this strong error should decrease with HL to the eta S. And the last assumption that we already had before is that the total work is proportional to the H to the minus gamma. Okay, now I rewrite here the collection of data, capital Y, as capital G plus epsilon. And this capital G is just GL times the identity. It's just to simplify notation. Okay, as we did before, we said that the expected information gain was the integral or the expectation of Z of the function Z, sorry. And here we have the expected information gain at the level L is defined as the expectation of the functional ZL. And again, basically what we do is in this last expression is we replace G by GL. So we do the same with the approximated evidence. We replace basically G by GL. And here RL is just the ratio between the prior and the posterior approximated using the Laplace approximation. Okay, again, just to simplify notation. So now we consider a sequence of L plus 1 meshes. And these meshes have different size, and the size is HL. As we increase L, the mesh gets finer and finer. Usually we use a geometric sequence with a factor of 2. So we refine the mesh by a factor of 2. As we show in the last expression, HL is equal to beta to the minus L times H0, and beta is usually 2. And we now can define the expected approximation gain at level L. That means is the finest level as a telescopic sum of the expectation of delta ZL. And the delta ZL here, represented in the second equation, is the difference between the result between two different meshes using the same underlying realization. So it's the same randomness. The only change here is the mesh. So since the underlying realization here, it will be the same it will be different for each level. We consider these levels independent when we take the sample-based version. So as you can see here, we obtain the sample-based version or the Monte Carlo version of the evidence using Monte Carlo as we did before. And now we use the hat to denote that this is a sample-based version. And the same with the function f, which is the log ratio. And now we can define the statistical estimator multi-level double loop Monte Carlo. So this statistical estimator is basically the sample version of this first expression that we have here. The first term is for the level 0, and that means that there is no difference. As we can see here, when we are in the level 0, we have no difference. Is only we use the functional ZL. And from level 1 to capital L, we have the Monte Carlo, let's say, of these differences. And here, the underlying realizations are the same for every level. As we change the level, they are independent. So as we did before here, we can split the error into a bias and a variance error, or statistical error. So the bias has, again, two components, one related to the mesh, but now is only related to the finest level. So that means that the error of this statistical estimator related to the mesh depends only on the finest mesh. And we have this extra bias, which is related to the inner integral, ML, and is related to the last level as well. And the variance, since the Monte Carlo at every level are independent, we have at the end the sum of the variances of each Monte Carlo. So these VLs, they are denoted here in the last expression, and is basically the variance of this difference between FL and FL minus 1. Just let's spend some time here in this FL and FL minus 1. As you can see here, theta ln is the same input for both. Okay. However, here YL, and I am looking at the upper index, we have YL for the FL, and we have YL minus 1 for the FL minus 1. That means that we are computing using a model with a mesh that is HL minus 1 for the FL minus 1 and with HL for FL. Okay, so we are using here different meshes, the same underlying random realizations. But you can see here also that for the inner loop, we have different sizes in the random realizations. Here we have in FL we have ML, and in FL minus 1 we have ML minus 1. So this is an extra ingredient that we have when we came up with this multi-level double loop Monte Carlo. So in our second paper, we got this upper bound for the variances. It basically tells us that the variances VL, which is the one that we were looking at before, these ones, the upper bound is related to HL and to ML. And the total work here is similarly as before, but is a summation over all the levels of NL times ML times the work of each model GL. So now we can try to optimize these parameters, and I say we can try because we couldn't get a closed form when we try to find the optimal number of inner and outer samples as well as the mesh size. So what we did, we did the following. We said, okay, let's split the bias into components, and let's put half of it for each part of the tolerance. So that's why we have 1/2 here. Just recalling that kappa is the splitting factor between the error, between the variance and the bias. And here the 1/2 is related to an extra split that we do between these two biases. Of course, when we do this, we can solve these two constraints and we can get the optimal number of levels, L star, and we can get kappa star. And we can get as well the number of inner samples. And again, the number of inner samples is proportional to tau to the -1. And here, and I will, as I showed you before, when we use the Laplace approximation in the inner sample, the integral is very well approximated using only one sample. So what we did here, we committed the crime and said, okay, our sequence of MLs are the same and are equal to the final one, M capital L, which is this one, the first that we are defining here. And assuming this, we specialized our first theorem to this relation here. So the VLs, the upper bound is related to H to the strong convergence rate and H to the weak convergence rate. And then now with these constants, with these parameters, we can optimize the problem with respect to only NL. And what we get is something pretty similar to the classical multi-level Monte Carlo estimator. And as I said before, we aim at a certain tolerance. So we want to, in probability, to be below a certain tolerance. And the total work to achieve that is given by this expression. So let me show you, I guess, only one example. So here we have, again, is the same problem, but now we have 4 plies. This is the cross section of this plate. And again, red is current influx and blue is current outflux. And we are aiming at recovering the fiber orientation of each ply. So this is the problem definition. Basically, we put a prior knowledge on these theta, which are uniform. So we assume that they vary uniformly. And the error are Gaussians, as we said before, and with variance here 10 to the -4. So this is just these two plots. They is just a confirmation that our assumptions are fine. So on the left, we basically are showing the EL, which convey information about the expectation of the different of the levels, and VL convey the information about the variance of these levels, and both decrease as we assumed. So if this is satisfied, the multi-level double loop Monte Carlo should work properly. And what I mean by that is that we should achieve the tolerance with a minimum cost, computational cost. This is the consistency plot showing that as we decrease the tolerance, the error decreases as well. And here we did for a confidence parameter of 5%. So that means that 5% of our simulations may give us some errors that are larger than our tolerance. And this is the average time. So here on blue, on solid blue, we have the multi-level double loop Monte Carlo, which is growing roughly with tau to the -2 log tau to the -1 squared. And of course, we are using importance sampling here. And in dash red, we have the double loop Monte Carlo with importance sampling. Here we have to use importance sampling, otherwise the computational burden, it's horrible. We cannot get anything reasonable. And for the multi-level Monte Carlo is way more critical, because if we do not use importance sampling, these two assumptions, that the strong convergence and weak convergence, they are not easily satisfied. You need to use a huge number of inner sample to satisfy these two assumptions. So that's why it's so crucial to use importance sampling here. And yeah, so this is what I wanted, the message I wanted to convey about the multi-level double loop Monte Carlo. Now I will show you another work that we did that I like very much, but I will just show very, very briefly. So is okay, we didn't, in the problem before, we didn't discuss how to actually find the best experiment. How do we optimize the problem, and how we find the optimal experiment, the Xi asterisk. So this is can be posed as the argmean of expected value of a function. And what we usually can do here is, using deterministic algorithms, is to compute the gradient of this expectation and just run traditional algorithms. But we can use some different versions of optimization algorithms and use stochastic gradient algorithms, which we do not rely on computing the gradient of the expected value of this function, but we can compute just the gradient of the function for one realization or for a set of realizations. When we use only one, is the well-known stochastic gradient descent. And I just, in this work, we have basically two propositions where we show how we can compute this gradient for the Monte Carlo Laplace approximation and for the double loop Monte Carlo. Basically, the first one is we just have to show that the gradient of the measure in the outer integral vanishes, and in the second proposition, with few algebraic operations, we arrive that the gradient is related, and this is quite obvious, but the gradient is related to the principal values and the gradient of the principal values of the posterior distribution. And I will show you a very simple example here, where we have a beam loaded with a dead load Q0 or QO, I guess. Yeah. And we have to place a strain gauge in this beam. And this strain gauge measures deformation. And we want to recover the material properties of this beam by measuring this deformation. And we do the optimization here. And our starting point, this is the beam, okay, the bottom plot. And the isolines are the isolines of the expected information gain. And here we use three different algorithms. I'll not focus on that. And our optimal point is the blue dot. Okay, you can see here our prior is this gray Gaussian that you can see here on the top, and our posterior at the initial guess is the red one, and at the optimal point is the blue one. So you can see that the posterior concentrates a lot, and we can learn much more if we find the optimal experiment. And here, okay, I have another example. Here is again the electrical impedance tomography, and we want to find the optimal pattern flux, current flux to maximize the information we get from this experiment, right? In order to recover again the angle of the fibers. And yeah, basically on the left, you can see the blue, the gray one, which is a uniform prior. The red one is the posterior of the initial experiment, and the blue one, the which is very concentrated, is the optimized posterior. And on the right, we have the convergence of the design variables. And that was it. The first paper here is basically the first part of the talk. The second one is the multi-level double loop, and the third one is related to the stochastic optimization using Nesterov type of accelerations. Thank you very much.